Humanity stands on the verge of an economic revolution beyond Earth. The key to unlocking this future is fusion energy, the same power that fuels the stars. By the end of this, you will understand how fusion reactors will transform the entire financial model of space colonization. We will explore how this technology turns the impossible cost of living in space into a practical business plan, and how the solar system could become a new marketplace. What does it truly take for an economy to flourish in the void of space? The tyranny of the rocket equation dictates a brutal reality for space travel. To launch a single kilogram of material into orbit, you need a staggering amount of fuel, which itself has mass, requiring even more fuel in a vicious cycle. This fundamental law of physics makes every gram we send beyond Earth incredibly expensive. That high cost does not disappear once you arrive. In the vacuum of space, energy is the ultimate currency, and our current options are deeply flawed. Chemical fuels are a one-time use proposition, and solar power grows weak and unreliable the farther you travel from the sun. This energy scarcity creates an economic chokehold. Think about building a simple habitat. You need to launch every single beam, every bolt, every panel from Earth at a cost of thousands or even tens of thousands of dollars per kilogram. Now imagine needing to constantly resupply that outpost with air, water, and food, all hauled up from our planet's gravity well. This total reliance on Earth-based supply chains makes any dream of a self-sufficient colony impossible. It is an economic model built on a foundation of perpetual expense. Breaking this cycle requires more than just incremental improvement. It demands a complete rethinking of power generation in space, a leap to a technology that can provide immense, constant, and local energy. That is the paradigm shift fusion energy brings to the table. That colossal energy we need to break the economic chokehold comes from a process perfected by nature over billions of years. Nuclear fusion is the universe's ultimate power plant, the same engine that drives our sun. It works by forcing the nuclei of small atoms like hydrogen to smash together and merge, creating a new, heavier atom. In that moment of creation, a tiny amount of mass is converted into a staggering burst of pure energy, exactly as described by Einstein's famous equation. This is fundamentally different from the nuclear fission used in today's power plants. Fission splits large, heavy atoms apart, a process that generates dangerous, long-lived radioactive waste. Fusion, by contrast, is a far cleaner and safer prospect. Its primary waste product is harmless helium, the same gas we use to fill party balloons. The most researched fusion reaction uses two heavy forms of hydrogen called deuterium and tritium as its fuel. Deuterium can be extracted from seawater, while tritium can be bred from lithium, a common metal. This means the fundamental ingredients for star power are astonishingly abundant right here on Earth, and we have strong evidence they exist on the Moon and asteroids as well. To truly grasp the revolution this represents, consider the energy density. A single gram of fusion fuel can release as much energy as burning 10,000 kilograms of coal. This is not a simple upgrade, it is a leap into an entirely new category of power. Mastering this reaction means holding the key to a nearly limitless energy supply, and that key is what unlocks every closed door in our solar system. This abundance of fuel changes everything. The very ingredients for star power are not rare treasures locked away on Earth. They are scattered almost everywhere we might want to go. Deuterium, one of the key fuels, can be extracted from simple water. Its partner, tritium, can be generated right on site by using the neutrons that the fusion reaction itself produces, interacting with a common metal called lithium. And when we look out across our solar system, we find water ice in the shadowed craters of the Moon, buried in the red soil of Mars, and locked within countless asteroids. Lithium, meanwhile, is a cosmically common element. This simple fact transforms the entire financial equation for settling space. A fusion-powered colony would not be a patient on a life support line running all the way back to Earth. It would be a self-sufficient entity capable of mining its own water and processing its own lithium to create its fuel. This concept, called in-situ resource utilization, is the ultimate game changer. It means a spacecraft heading to the asteroid belt would not need to carry all the fuel for its entire mission from Earth. It could refuel at a depot on Mars, or even at a station orbiting Ceres, using propellant mined and manufactured on site. Distant worlds and asteroids cease to be barren rocks and become strategic gas stations for the solar system economy. The ability to live off the land is the fundamental break from the old, expensive model. It is the first and most critical step toward true economic independence, turning the infinite void from a prison of scarcity into a frontier of limitless possibility. So how do we translate this potential energy into tangible industry? This propulsion revolution begins by shattering the most fundamental limitation in space travel. Imagine a spacecraft that no longer needs to dedicate 90% of its mass to chemical fuel tanks. Fusion power makes this possible. A fusion rocket operates on a principle of pure, efficient power. Instead of burning chemicals for a short, violent burst of thrust, it uses magnetic fields to channel the immense energy of fusion reactions, ejecting a superheated plasma out the back at a significant fraction of the speed of light. This is the magic of specific impulse, a measure of engine efficiency. Today's best chemical engines have a specific impulse measured in the hundreds of seconds. A fusion drive could achieve tens of thousands, even hundreds of thousands of seconds. This is not a minor improvement. It is like comparing a horse-drawn cart to a modern jet aircraft. The implications are staggering. A trip to Mars, which currently takes 6 to 9 months one way, could be reduced to a matter of weeks. A journey to the resource-rich asteroid belt, once a multi-year epic, could become a routine commercial run lasting only months. This compression of time and distance changes everything. It makes the solar system feel smaller, more connected, and far more accessible. Suddenly, shipping platinum from an asteroid is not a decade-long speculative venture. It is a manageable logistics operation. Ferrying colonists to Mars is no longer a life-risking, one-way mission. It becomes a commute. This is the birth of a true interplanetary economy, all powered by the engine of a star. That robust, growing city in space needs a heart that never stops beating. A permanent colony is far more than a shelter. It is a living, breathing organism that consumes power every single second. For life support systems to scrub carbon dioxide from the air and reclaim every drop of water, for the vast indoor farms that must feed thousands under artificial suns, the demand for electricity is colossal. Solar panels alone cannot meet this need, especially during the long lunar nights or through the dust storms of Mars. Fission reactors present their own burdens of heavy shielding and radioactive waste. A single, compact fusion reactor solves this. It can deliver gigawatts of power with the steady, unwavering rhythm of a star, day and night, season after season. This constant energy river enables closed-loop systems that operate not just efficiently, but perfectly. Imagine a habitat where the air you exhale today is purified and returned to you tomorrow, where the water you use is endlessly filtered and recycled. Envision cavernous agricultural modules illuminated by powerful lamps, where crops grow in carefully controlled atmospheres, producing enough food to sustain an entire population without a single resupply mission from Earth. This is the transition from a fragile outpost perpetually on the edge of failure to a thriving, self-sufficient metropolis, when the colony no longer spends its energy and resources just struggling to survive. Its people are freed to do what people do best: create, build, and innovate. They can turn their attention outward to the real economic potential waiting in the soil and rocks around them. This shift from survival to production marks the dawn of a true extraterrestrial economy. The immense, constant power from a fusion reactor transforms local dirt and air into a construction yard and a fuel refinery. On the Moon, a processing plant bathed in the glow of fusion heat could melt the dusty regolith, a process that requires phenomenal energy. From that molten rock, it would extract pure, breathable oxygen and valuable metals like aluminum and iron. These are not just abstract resources, they are the very beams for habitats, the wiring for power grids, and the raw materials for machinery, all manufactured on site. The same revolution unfolds on Mars. The thin Martian atmosphere is mostly carbon dioxide. With enough power, a facility can split this carbon dioxide into oxygen for colonists to breathe and carbon monoxide that can be used as a propellant. This is the core of in-situ resource utilization, and fusion energy is the key that makes it all work. The high energy cost that always made these processes impractical simply vanishes. Why spend millions to launch a single solar panel from Earth when you can manufacture an entire array from metals you dug out of the ground next door? This is the pivotal economic transition. A fusion-powered colony stops being a money pit, a constant drain on resources that requires everything to be shipped from home. It becomes a net producer. It builds its own infrastructure, grows its own food, and manufactures its own goods. It can even produce a surplus, creating oxygen, water, or refined metals to sell to passing spacecraft or other settlements. This is how a colony pays for itself, and it all starts with the power to turn barren soil into a foundation for prosperity. These newly forged metals and manufactured goods are the foundation of a new marketplace, but the real wealth lies further out in the darkness. The asteroid belt contains more mineral riches than our entire planet, a treasure trove locked inside countless floating mountains. For decades, extracting those resources was a fantasy, a dream crushed by the immense energy required to reach, process, and return them. Fusion power shatters that barrier. A single fusion-powered mining vessel becomes a mobile factory. It journeys to a metal-rich asteroid, and its reactor provides the staggering power needed to run industrial-scale drills, massive crushers, and intense smelters right there on site. Instead of hauling useless rock across the solar system, the ship refines the raw ore into pure, dense ingots of platinum, gold, and rare earth elements. These are the critical materials for advanced electronics and green technologies back on Earth. But the real magic happens with the water ice also found in many of these asteroids. The same fusion reactor provides the power to split that water into its basic components, hydrogen and oxygen, the most powerful chemical rocket fuel there is. One mined asteroid can thus become a fueling depot, producing thousands of tons of propellant to power the next wave of spacecraft. This creates a self-feeding economic engine. The fuel from one asteroid allows a miner to reach a second, more distant rock. The metals mined from that second asteroid pay for the mission and fund the construction of more mining ships. This is no longer a linear, Earth-dependent operation. It is a self-perpetuating cycle of growth, an industrial revolution born in the void. The economics shift from impossibly expensive to wildly profitable, attracting vast private investment and finally unlocking the solar system's true potential. The ultimate expression of this self-feeding economy might not be found on distant planets, but right in orbit around our own. The unique environment of space, its permanent state of microgravity, is a perfect vacuum for manufacturing miracles. Here, away from the distorting effects of Earth's gravity, we can create things of impossible perfection. We can grow flawless crystals for the next generation of supercomputers, blend exotic alloys that do not separate into layers, and formulate new pharmaceuticals with a purity that is unattainable in any lab on the planet. But these orbital factories are ravenous beasts. They demand a constant, immense flow of power to run furnaces, supercomputers, and life support around the clock. Solar power has a rhythm, a cycle of day and night that interrupts these delicate processes. This is where the fusion reactor finds its ultimate industrial calling. A single reactor stationed at an orbital hub can deliver the unwavering gigawatts needed to power a constellation of factories, all operating 24/7. This transforms the concept from a handful of experimental labs into a full-blown industrial revolution in the sky. The goods produced in this zero-gravity environment are not just novelties. They are high-value products that are either impossible to create on Earth or so expensive that they remain laboratory curiosities. Think of perfect ball bearings for the most sensitive machinery or fiber optic cables of unimaginable clarity. These products can be shipped down the gravity well to Earth, where they command premium prices, or they can be used to build even more advanced infrastructure in space itself. This creates a new economic loop, a supply chain that begins and ends in the void, completely independent of terrestrial industry. Our orbit ceases to be a passive highway and becomes a vibrant, humming center of production, a place where the unique properties of space are not an obstacle to overcome, but the most valuable asset of all. This plunge in energy cost is the single greatest economic transformation waiting in the wings. Right now, generating a single watt of power in orbit is a staggeringly expensive endeavor. Every solar panel, every battery, every component has to be launched from Earth at monumental cost. Fusion energy promises to shatter this paradigm, making megawatts of power not just available but cheap. Think of it as the difference between buying water by the thimbleful versus tapping into an ocean. This new abundance of affordable energy sends ripples through the entire space economy, fundamentally altering the math for every single operation. Suddenly, the energy-intensive process of baking oxygen out of moon dust is no longer a costly experiment. It is a routine industrial procedure. The immense power needed to smelt aluminum from a metallic asteroid is no longer a deal breaker. It becomes a competitive advantage over terrestrial mines. Even the constant hum of life support on Mars, the recyclers that purify every drop of water and every breath of air, transitions from a major power drain to a negligible operational expense. This is the cascading effect of cheap energy. It unlocks a powerful positive feedback loop. As energy costs fall, more industries become viable. These new industries build more infrastructure, which in turn creates a greater demand for even more energy. This self-reinforcing cycle is the very engine of an economic boom, a boom born not on Earth but forged in the vacuum of space, all ignited by the power of a miniature star. This ability to build big rewrites the future of human civilization in space. We have long dreamed of vast, rotating space habitats, enormous cylinders spinning to create their own gravity, with landscapes and cities housed inside. These are the O'Neill cylinders of science fiction, capable of supporting millions of people. Until now, they were purely theoretical, not because we lacked the engineering vision, but because we lacked the economic and energetic means. The sheer scale is difficult to comprehend. We are talking about moving and processing millions upon millions of tons of metal, rock, and glass. With today's energy sources, the cost of simply powering the construction would be astronomical, a literal non-starter. But a single compact fusion reactor changes that entire calculation. It provides the concentrated power to run massive orbital shipyards, to energize industrial lasers that can weld mountains of steel in the vacuum of space, and to operate the fleets of robotic fabricators that would assemble these behemoths piece by piece. Suddenly, the impossible becomes a complex but solvable engineering problem, one with a clear economic pathway. These are not just shelters, they are new worlds, and with fusion energy, we can finally afford to build them. What kind of society emerges inside these engineered ecosystems? They become the ultimate centers of commerce, with entire industries dedicated to maintaining and expanding the habitat itself. They become hubs for tourism, offering experiences of zero-gravity sports and breathtaking orbital vistas that no planet can match. They become campuses for pure research, laboratories operating in a perfectly controlled environment, free from weather, earthquakes, or pollution. This creates an entirely new real estate market, one not bound by the limited surface area of a planet. The value is no longer in the land, but in the structure itself, in the volume of habitable space that can be created and sold. The ability to build large is fundamentally the ability to think big, to envision an economy and a society that is no longer confined to the ancient surfaces of moons and planets, but is free to grow and evolve in the vast emptiness between them. A thriving economy is built on more than just goods and energy. It runs on information. The nervous system of this new interplanetary marketplace will be a communication network of unimaginable speed and reliability, one that makes our current internet look like a series of tin cans connected by string. Today, we use radio waves to talk to our robots on Mars, a method that is agonizingly slow. A single high-definition image from the red planet can take half an hour to download. This delay, known as latency, makes real-time control impossible. You could not operate a delicate mining drill on an asteroid from Earth if your commands take 45 minutes to arrive. For an economy to function across millions of miles, this data bottleneck must be shattered. The solution lies in shifting from radio to light. Laser communication systems can transmit data at rates thousands of times faster, beaming entire libraries of information between planets in the time it takes to brew a cup of coffee. But these powerful laser arrays are not simple flashlights. They are ravenous for energy, requiring a steady, immense flow of electricity to fire their tightly focused beams across the void. This is where the fusion reactor becomes the silent, indispensable partner. Only a fusion power source can provide the constant, gigawatt-level base load needed to keep these interplanetary data highways illuminated 24/7. Picture a network of laser terminals perched on the rim of a lunar crater, stationed in orbit around Mars and dotted across relay satellites positioned throughout the inner solar system. Each one, powered by its own compact fusion reactor, acts as a supercharged router in a celestial internet. The economic possibilities this unlocks are transformative. A financier in London could execute a stock trade on a Martian exchange with no perceptible delay. A surgeon on Earth, wearing a haptic feedback suit, could perform a delicate operation on a patient in a Jovian moon base, their movements mirrored in real time. Teams of engineers could teleoperate a fleet of autonomous mining bots on the metallic asteroid Psyche, watching through high-definition video feeds as if they were standing right there in the pit. This seamless, instantaneous flow of data is what binds isolated outposts into a single, cohesive economic zone. It turns the solar system from a collection of lonely islands into a networked community, where distance is no longer a barrier to commerce, collaboration, or simple conversation. This grand vision of a networked solar system economy finds its ultimate expression in a project of almost unimaginable scale. We are talking about terraforming, the deliberate engineering of an entire planet to make it more like Earth. For Mars, this means a centuries-long process of warming its frozen surface, thickening its wispy atmosphere, and perhaps even generating a protective magnetic field. Each of these steps demands energy on a planetary scale, a level of consumption that has always rendered the concept a pure fantasy. But a network of fusion reactors changes the economic calculus entirely. These power plants dotted across the Martian plains could provide the relentless gigawatt output needed to run colossal atmospheric processes, machines that would pull greenhouse gases from the very soil and pump them into the air. They could power orbiting mirrors the size of cities, focusing sunlight onto the polar ice caps to melt them and release vast reservoirs of frozen water and carbon dioxide. This would initiate a runaway greenhouse effect, a controlled and deliberate version of what we fear on Earth, slowly thickening the atmosphere and raising the planet's temperature. The energy required for just the first phase of this transformation is beyond any current technology, but it is precisely the kind of continuous, massive power that fusion is built to deliver. The upfront investment is staggering, a multi-generational commitment of resources that would dwarf the gross domestic product of every nation on Earth combined. Yet the long-term economic payoff is arguably the greatest in human history. A second Earth-like planet with a breathable atmosphere, liquid water on its surface, and a temperate climate would open a frontier for settlement, agriculture, and industry larger than all the continents of our homeworld combined. The value of that new real estate, those new farmlands, and those entire new cities is incalculable. Fusion energy does not make terraforming easy or quick, but it does something far more important. It makes the first foundational steps economically plausible, turning a dream of science fiction into a conceivable, if distant, goal for our species. It reframes this grandest of projects not as a cost, but as the ultimate long-term investment in the future of humanity. Generating that immense power is only half the battle. You must also deliver it without wasting a single watt. On a planetary scale, the resistance in ordinary copper wires would bleed away a fortune in energy as useless heat before it ever reached a distant mining outpost or manufacturing dome. This is the silent enemy of any large-scale economy, an invisible tax on every transaction and operation. The solution flows through a revolutionary material, high-temperature superconductors. Unlike the classic superconductors that need to be chilled to temperatures near absolute zero, these advanced materials achieve their magic at much more practical, higher temperatures. When cooled, they exhibit a property that seems to defy physics. They conduct electricity with absolutely zero resistance. This means a current can flow through a superconducting cable forever without losing any energy at all. The implications for building a civilization are profound. On an airless world like the Moon, you could run a grid of these cables across the entire surface, using the pervasive cold of shadowed craters to keep them chilled. A single, massive fusion reactor at the lunar South Pole could then power every habitat, every factory, and every research station on the near side, the far side, and everywhere in between, with no loss of power over hundreds of miles. This creates the circulatory system for the entire colonial economy, a network of energy arteries that makes power as reliably available as the air you breathe. Efficient distribution transforms energy from a localized resource into a universal utility, the indispensable bedrock upon which every other industry is built. This new economy will be built not on the scarcity we know, but on a foundation of radical energy abundance. The very nature of trade and commerce must be reinvented when the fundamental cost of power plummets towards zero. Imagine a future where settlements do not trade in dollars or digital coins, but in units of energy itself. A thriving colony on Mars might pay for a shipment of advanced medical equipment from an orbital factory by transmitting a block of energy credits, a direct promise of gigawatt-hours of fusion power delivered to the factory's grid. Energy becomes the universal currency, the gold standard for a solar system where tangible goods are manufactured locally, but power is the ultimate fungible commodity. This shift ripples through every business model. Why would a lunar mining corporation spend its capital to own and maintain its own fleet of massive interplanetary freighters? It is far more efficient to contract with a specialized company offering propulsion as a service. A fusion-powered tug, essentially a nimble star with a docking clamp, would latch onto your cargo container and haul it from lunar orbit to a Martian transfer station for a fee. The mining company pays for the movement, not the machinery, transforming capital expenditure into a predictable operational cost. This is the space-age equivalent of container shipping, where you pay for the journey, not the entire ship. Such a complex web of trade demands entirely new forms of financial infrastructure. The insurance industry, for instance, will undergo its own revolution. An insurance policy for a shipment of refined platinum traveling from the asteroid belt to Earth orbit will not be a simple form. It will be a sophisticated financial instrument that calculates risk based on trajectory accuracy, the reliability of the tug's fusion reactor, and even the predicted activity of solar flares. The first company to successfully underwrite interplanetary cargo will become the Lloyd's of London for the solar system, managing trillion-dollar risks. This new frontier will also force us to rewrite the very concept of property law. Who owns an asteroid after a mining company has begun extracting its resources? Does a corporation have the right to claim an entire metallic world, or just the portion it actively mines? Can you own the sunlight over a specific patch of the lunar surface for your solar farm, or the mineral rights beneath a crater on Mars? The old terrestrial models of borders and deeds are utterly useless. We will need a new legal framework, one developed by diplomats and corporate lawyers in tandem, to prevent conflicts and establish clear, enforceable rights in the void. The most successful entrepreneurs in this new landscape will not be the ones who simply mine the most platinum, but those who devise the most clever systems for managing this unprecedented abundance. They will be the architects of the energy credit clearinghouses, the designers of the standardized contracts for propulsion services, and the pioneers of off-world corporate law. The economic landscape of our solar system will be as alien and challenging as the vacuum of space itself, a blank slate waiting for a new generation of innovators to write the rules. This new energy currency will inevitably redraw the map of global power. The first entity to successfully deploy a practical fusion reactor beyond Earth will seize an advantage unlike any other in history. It would instantly become the default utility provider for the entire space economy, the one company or country that powers every satellite, fuels every freighter, and energizes every fledgling colony. This is not merely a market position, it is a form of strategic leverage that transcends borders. The nation that controls the primary energy nodes in cislunar space, for instance, holds the keys to the inner solar system. Its currency, its trade agreements, and its technical standards could become the bedrock of off-world commerce. This creates a new axis of geopolitical influence, where power is measured not in nuclear warheads, but in gigawatts delivered to critical infrastructure. The politics of oil and gas that have defined the last century on Earth will be replayed on a far grander stage, with the entire solar system as the theater. Yet the sheer monumental cost and complexity of this endeavor might also force a different outcome. No single corporation or country may be able to bear the burden alone for long. We could see the rise of unprecedented international consortiums, alliances formed not for mutual defense, but for mutual development. Imagine a partnership between old terrestrial rivals, pooling their resources and intellect to construct the first major fusion-powered shipyard at a Lagrange point. The incentives to cooperate could eventually outweigh the instinct to compete. Sharing the astronomical costs also means sharing in the universe-altering benefits, creating a network of interdependence that makes conflict in space an unaffordable luxury. The dawn of cosmic energy abundance presents humanity with a fundamental choice. Will we allow the old patterns of resource rivalry to define our future among the stars, or will the infinite possibilities of fusion power finally compel us to build a more unified and cooperative path forward? These engineering hurdles are not small, and it would be a mistake to ignore them. Containing a star is perhaps the greatest technical challenge humanity has ever faced. We are attempting to bottle a substance hotter than the sun's core, a roiling plasma that will instantly vaporize any physical container it touches. We hold it in place with invisible walls made of pure magnetic force, but keeping that magnetic bottle perfectly stable is a delicate and relentless task. The smallest instability can cause the plasma to wobble, touch the reactor wall, and extinguish in an instant. Doing this not in a massive, ground-based laboratory, but within a reactor compact and robust enough to be launched on a rocket and operated autonomously for years in deep space, multiplies the difficulty exponentially. Then there is the relentless bombardment. A fusion reaction is a torrent of high-energy neutrons, atomic shrapnel, that flies right through magnetic fields and slams into the reactor's inner structure. Over years of operation, this neutron radiation makes metal brittle and weak, like glass that has been left in the sun for too long. We need entirely new classes of advanced materials, alloys and composites that can withstand this atomic assault for decades without failing. The sheer scale of the initial investment is another formidable barrier. The research and development costs alone are measured in the tens of billions. Then you must factor in the astronomical expense of building the first flight-ready units and launching them into space, a venture that could easily consume the annual budget of a small nation. Yet, despite these monumental challenges, the race is on. Why? Because the economic prize at the end is a complete rewrite of the rules for our civilization. The potential is so transformative that both government space agencies and private capital are pouring unprecedented resources into the problem. They are not just dreaming, they are building and testing. New alloys are being developed and irradiated in test reactors. Innovative magnetic confinement designs are being modeled on supercomputers. Each experiment, even those that fail, teaches us something new, bringing us one step closer to a solution. Acknowledging the sheer scale of the challenge is not an admission of defeat. It is the first and most necessary step in any great engineering endeavor. It is the process of mapping the mountain before we begin to climb. This transformation will not arrive overnight. The journey from our current experimental reactors to a full-blown fusion economy in space is a marathon of engineering and perseverance, not a simple sprint. Right now, our focus is firmly on Earth, with massive projects like the International Thermonuclear Experimental Reactor striving for that first crucial milestone, a sustained reaction that produces more energy than it consumes. Achieving net energy gain is the fundamental proof of concept, the spark that must be struck before we can build a fire. But the reactors of this era are behemoths, complex scientific instruments confined to their terrestrial laboratories. The next great leap will be one of miniaturization and ruggedization. We must re-engineer that success into a compact, robust machine that can survive the violent shaking of a rocket launch and then operate flawlessly in the vacuum of space for years without a maintenance crew. This is the challenge of creating a space-rated prototype. We might see the first of these tested in the relative safety of low Earth orbit within the next 2 or 3 decades, a critical demonstration that fusion can work beyond our atmosphere. A lunar test is another logical step, using the Moon's surface as a proving ground under partial gravity. These initial prototypes will not power cities. They will be the trailblazers, providing vital electricity for a small orbital workshop or a fledgling lunar base, proving their reliability 1 kilowatt-hour at a time. This gradual, step-by-step approach is not a sign of slow progress. It is the only way to build confidence in a technology that must be 100% dependable. The expansion of our cosmic footprint and the maturation of fusion power are on parallel tracks. As we plan for a permanent outpost on Mars in the coming decades, the fusion reactors destined for it will be evolving in lockstep, growing more powerful and reliable with each successive iteration. Widespread deployment, the kind that could energize an entire Martian city of thousands, is likely a 50-year horizon. This long-term vision requires immense patience, but the payoff is a steady, predictable decline in the cost of doing business in space. Each new, more efficient reactor that comes online makes the next industrial venture a little more affordable, a little less risky. The first prototype enables a small-scale ice mining operation on the Moon. That successful mining operation funds a larger fuel depot, which in turn makes asteroid prospecting economically viable. It is a cascade of opportunity where each achievement, powered by a little more fusion energy, builds the foundation for the next great leap. The weight is not empty, it is filled with a constant drumbeat of progress, each milestone bringing us closer to the day when the economics of space finally, irrevocably, flip in our favor. This expansion into the cosmos offers a profound and unexpected gift for our home world. The relentless industrial activity that powers our modern civilization comes at a steep environmental cost on Earth, scarring landscapes and filling the atmosphere with carbon. But what if we could relocate the very heart of that industry off-world? The most energy-hungry processes, like smelting metals from ore or manufacturing high-performance alloys, are also the most polluting. In a space-based economy, these operations are naturally shifted to where the energy is cheapest and most abundant, inside the asteroid belt or in high orbit. The billowing smokestacks of a 20th-century steel mill are replaced by the controlled plasma of a zero-gravity foundry, its waste products vented safely into the infinite vacuum. The environmental impact of these activities, while not zero, is removed from Earth's delicate and interconnected biosphere. Our planet's atmosphere, soils, and oceans would no longer bear the burden of our material growth. This is not merely about moving a problem, it is about solving it by changing the entire context of industry. The economic incentive to mine asteroids for platinum suddenly becomes an ecological win, sparing a terrestrial landscape from being torn open. The financial logic that drives us outward could, paradoxically, be what allows the natural world back home to finally breathe and heal. This clean separation could go even further, with the potential to actively send power home. While it sounds like science fiction, the concept of beaming energy from space is grounded in real physics. Vast satellites in geostationary orbit, each powered by its own massive fusion reactor, could collect sunlight 24 hours a day without any atmospheric interference. They would convert that energy into microwave or laser beams, transmitted with pinpoint accuracy to receiving stations on Earth. These rectennas on the ground would then convert the beams back into electricity, feeding a constant carbon-free stream of gigawatts directly into the global power grid. Unlike terrestrial solar and wind, this source would be completely reliable, unaffected by weather or the cycle of day and night. It would provide the bedrock base load power that renewables struggle to deliver, ultimately making fossil fuels obsolete not through sacrifice, but through sheer economic and energetic superiority. The development of a space economy, therefore, stops being a separate ambition from environmentalism. It becomes one of the most powerful tools for planetary stewardship we have ever conceived. The economic engine that builds cities among the stars could be the very same force that finally allows us to restore the blue-green jewel we first called home. This new economy will demand a workforce unlike any seen before. Think of the lunar prospector, bundled in a heavily insulated suit, guiding a robotic drill rig across the gray dust of the moon's south pole. Their quarry is not gold or silver, but helium-3, a rare isotope that could fuel the next generation of even cleaner fusion reactors. Back on Mars, the most vital professional in any settlement is the fusion reactor technician, a master of plasma physics and advanced engineering who keeps the colony's artificial heart beating. High above them all, in a control center orbiting Earth, the Orbital Traffic Controller monitors a three-dimensional display, directing the flow of fusion-powered tugs, automated freighters, and passenger liners along the busy interplanetary shipping lane. These are not the jobs of today, they are the specialized, high-skill careers of a spacefaring civilization, and they will command salaries and prestige to match their immense responsibility. With survival no longer the primary focus, human creativity will be unleashed. Artists will use the abundant energy to craft immersive virtual realities that let you walk on the surface of a gas giant or swim in the oceans of Europa, experiences sold as digital commodities across the solar system. Musicians will compose symphonies in zero gravity, their performances broadcast in real time to audiences on multiple worlds. This flourishing of culture creates entirely new markets. A company might specialize in designing custom virtual environments for wealthy patrons on Ceres. Another could produce high-definition holographic art installations specifically for the curved walls of rotating space habitats. Educational institutions will offer courses in asteroid geology or exobotany, taught by instructors living on Mars, their knowledge accessed through the high-bandwidth laser network. The very definition of leisure expands when your backyard is the cosmos. Tourism will explode, offering everything from week-long stays at a lunar resort to adrenaline-fueled excursions flying through the rings of Saturn in a shielded craft. This cultural shift is not a side effect of economic growth, it is the engine of the next phase. A society that has moved beyond mere existence will crave new forms of expression, new ways to learn, and new experiences to define their lives. This demand for art, entertainment, and self-improvement will fuel a consumer economy as dynamic and diverse as the people it serves. This new frontier of unimaginable wealth will be shadowed by equally staggering risks. A single fusion reactor on Mars represents a capital investment larger than many terrestrial cities, and its failure would mean the end of the colony it powers. An interplanetary freighter carrying 1,000 tons of refined platinum from the asteroid belt has a cargo value that could sway the global economy. You cannot simply call a tow truck if its magnetic confinement field falters halfway to Earth. The entire economic framework of this new age will rest on its ability to manage and ensure these monumental bets. The classic insurance model, built on historical data and predictable perils like storms or fires, is useless here. How do you calculate the annual premium for a plasma disruption event on a reactor design that has never existed before? What is the actuarial table for a micrometeoroid puncturing a fuel tank in the main asteroid belt? These are not simple questions. They are fundamental puzzles that must be solved before the first trillion-dollar investment is secured. The answers will not come from human intuition alone, but from a new generation of predictive artificial intelligence, modeling every conceivable variable across millions of simulated missions. This relentless drive to quantify the unquantifiable will, in turn, reshape the very technology it seeks to protect. To secure an insurable rating, a fusion-powered hauler will need more than just a robust engine. Its design will be dictated by redundancy. It might feature multiple, smaller reactor cores, any one of which can power the ship home if another fails. Its critical components will be surrounded by self-sealing compartments and layers of Whipple shields, sacrificial buffers designed to vaporize incoming debris before it strikes the primary hull. The insurance premium itself becomes a powerful design constraint, a financial force pushing engineers toward ever greater levels of inherent safety and resilience. This symbiosis between finance and engineering creates a powerful feedback loop for innovation. The need to minimize risk and lower those colossal premiums will spur the development of an entire ecosystem of autonomous repair systems. Imagine a swarm of spider-like drones permanently stationed within a reactor's service bay, capable of deploying the moment a sensor detects anomalous wear on a magnetic coil. Using advanced sintering lasers, they could patch and reinforce the component in place without ever requiring a human shutdown. For a spacecraft, a separate class of nimble, single-purpose repair tugs would lie dormant in orbital depots, ready to be dispatched at a moment's notice to a vessel in distress, performing emergency welds or conduit rerouting to avert a total loss. These are not luxury features, they are the mandatory safety systems required to make a policy even remotely affordable. The emergence of a stable, predictable insurance market is the final piece of the puzzle that unlocks mainstream capital. Pension funds and large investment firms, the entities with the deep pockets needed to fund a Martian city, are inherently risk-averse. They will not commit their capital to a venture that could be wiped out by a single piece of space dust. A reliable insurance backstop transforms a wildcat speculation into a manageable, if high-stakes, infrastructure project. It provides the confidence that allows a bank to issue a 30-year bond for an orbital factory, secure in the knowledge that a total loss is a recoverable event, not a financial apocalypse. In this way, the dry, complex world of actuarial science and risk underwriting becomes the silent, indispensable guardian of the entire cosmic economy, the foundation that makes all other grand ambitions financially possible. This relentless drive for safety and profit will be matched only by an insatiable hunger for knowledge. The very act of building a civilization among the stars will ignite an educational and research boom unlike anything in human history. Think of the university campuses of the future, no longer confined to Earth. Their most prestigious programs will be taught in orbital stations or on the lunar surface, offering advanced degrees in fields that sound like science fiction today. A student might major in plasma containment dynamics, learning to stabilize a miniature star, or in exogeology, specializing in the mineralogy of metallic asteroids. These are not niche interests, they are the core disciplines of a spacefaring species, and the demand for these skills will be astronomical. The research opportunities will be the real draw. A fusion-powered outpost on Mars is not just a colony, it is the ultimate laboratory, shielded from Earth's magnetic field and with limitless energy at its disposal, it becomes a perfect place to study the deepest mysteries of the universe. Physicists could construct particle accelerators larger than any possible on Earth, probing the fundamental forces of nature in the planet's low gravity. Biologists would have the power to run vast, sealed biospheres, testing theories of ecosystem development and perhaps even discovering the first clues of alien life in the Martian subsurface or in the subsurface oceans of moons like Europa. Every crater on the Moon and every canyon on Mars becomes a potential field site, a new chapter in the story of our solar system waiting to be read. This pure research will not exist in a vacuum. The challenges of surviving and thriving in space will force innovations that ripple back to Earth. The advanced life support systems perfected for a Martian city could lead to revolutionary water purification technologies for arid regions on our home planet. The new materials developed to withstand neutron radiation in fusion reactors might yield stronger, lighter alloys for everything from medical implants to safer automobiles. This creates a powerful feedback loop where the knowledge gained in the void fuels further technological advances, which in turn make life in space easier and more profitable. The pursuit of understanding our new environment becomes a major economic sector in its own right. Grants from terrestrial institutions, corporate funding for applied research, and tuition from off-world universities will generate immense revenue. The data collected by a research station on Titan about its hydrocarbon lakes could be sold for billions to chemical companies seeking new catalysts. A single discovery, like a novel extremophile microbe, could spawn an entire new branch of the biotechnology industry. In this knowledge economy, information itself becomes the most valuable export, and the entire solar system transforms into a classroom and a laboratory without walls. The final and perhaps most profound economic shift will be the complete democratization of space itself. For the entirety of the space age, access to the cosmos has been a luxury afforded only to the largest governments and a handful of the world's richest individuals. The sheer cost of building a rocket and buying the fuel has been an impenetrable barrier, a locked door keeping out almost everyone else. Fusion power shatters that door. When the cost of launching a kilogram of payload plummets and the price of moving that payload across the solar system collapses, the economics shift from exclusive to inclusive. Think of it as the difference between the era of the mainframe computer, a machine only a major corporation or university could own, and the arrival of the personal computer, which put incredible computational power on your desk. Fusion energy is the personal computer for the solar system. A small biotechnology startup will no longer need to beg for a tiny spot on a government-funded resupply mission to the space station. They can simply book a dedicated fusion-powered launch for their experimental lab, sending it to a commercial orbital facility where they can run their research for weeks or months. A university's planetary science department could fund a mission to send its own probe to study the plumes of Enceladus, a project that today would consume its entire endowment. Even a consortium of wealthy enthusiasts could pool their resources to fund a private expedition to the asteroid belt, not as tourists but as prospectors. This influx of new players, unburdened by the bureaucracy of a national space agency, will unleash a Cambrian explosion of innovation. The digital startup boom of the late 20th century was built on code and silicon, creating new industries from bits and bytes. The fusion-powered space boom will be its physical counterpart, built on atoms and energy, creating new industries from raw materials and manufactured goods. It is the difference between building a social media app and building a factory that prints custom satellites in orbit. When thousands of different entities, each with their own unique ideas and motivations, are all trying new things in the new environment of space, progress will accelerate at a dizzying pace. A crowded market is not just a competitive market, it is an endlessly inventive one, and for the first time in history, the greatest marketplace of all is about to open its doors to everyone. This intangible asset of confidence is the final, invisible pillar holding up the entire economic structure. Investors do not fund raw potential alone, they fund a believable future. A spreadsheet projecting profits from a Martian mining operation is just a fantasy if the power source for that operation is a fragile array of solar panels that could be silenced for weeks by a global dust storm. But replace that with a steady, humming fusion reactor, and the entire financial model shifts. That spreadsheet transforms from a speculative dream into a credible business plan. The perceived risk plummets, and when risk falls, so does the cost of capital. A loan to build a new processing plant on the moon no longer carries the interest rate of a desperate gamble, but that of a solid infrastructure project. This access to cheaper money is the oxygen that allows long-term ambitions to breathe and grow. We stop thinking in terms of temporary outposts designed for mere survival. With the energy question solved, the mindset of every colonist and every corporation shifts fundamentally. Instead of asking how we will generate enough power to scrub the air for the next month, we can ask what kind of school we should build for the children being born there. We can debate the design of a public park under a domed sky or invest in a local theater company. These are not frivolous expenses, they are the hallmarks of a society that believes in its own future. This psychological transition from a bunker mentality to a civic one is what turns a collection of habitats into a genuine community. It is the signal that life in space is no longer an extended emergency, but a new and permanent chapter for humanity. People plant trees whose shade they know they will never sit under, and that act, more than any balance sheet, proves that a true economy has taken root. This fusion-powered ecosystem thrives on a powerful symbiosis between human ingenuity and the machines that serve it. The immense, constant energy from a reactor does more than just light up a dome or power a life support system. It energizes the very brains of the colony, the vast arrays of supercomputers that would be impossible to run on solar or fission power alone. These are not ordinary computers. They are the home for the advanced artificial intelligence that manages the colony's every intricate function. One central AI might act as the planetary nervous system, constantly monitoring millions of data points. It balances the oxygen output from the algae farms with the consumption of the human population. It predicts maintenance needs for the water recyclers weeks before a component fails. It coordinates the power grid, diverting surplus energy to a metal refinery during off-peak hours, and then to a scientific lab running a complex simulation. This is not a luxury, it is a necessity for survival. No human team could process that much information in real time. The fusion reactor provides the raw power, and the AI provides the flawless, tireless intelligence to wield that power with perfect efficiency. But a brain needs hands. This is where the armies of autonomous robots come in, and they too are children of the fusion age. These are not the slow, cautious robots of today. A fusion-powered base can support entire fleets of them, operating around the clock. Imagine a construction site on Mars, where swarms of six-legged robotic builders assemble a new greenhouse, guided by the shared intelligence of the central AI. They do not need to stop for food or sleep, only to dock at a wireless charging station that draws its power directly from the city's fusion heart. In the mines, heavy robotic excavators work tirelessly, their operations synchronized to avoid collisions. their onboard processors calculating the most efficient way to extract ore without human guidance. This human-AI robot symbiosis creates a seamless economic engine. The humans set the vision and tackle the creative problems. The AI manages the colossal data and logistics, and the robots perform the physical labor in hazardous environments. The fusion reactor powers them all. A single project, like building a new landing pad, can be conceived by human engineers, designed and scheduled by the AI, and then executed by a coordinated robot workforce, all happening simultaneously. The acceleration of development is exponential. What would take a team of 100 astronauts years to build, this symbiotic system can accomplish in months. The whole truly becomes greater than the sum of its parts, forging a new kind of civilization where technology amplifies human potential instead of merely serving it. Our journey from a single, energy-starved planet to a vibrant, multi-world civilization hinges on this one profound ability to harness the power of the stars. Fusion reactors are so much more than just a new way to generate electricity. They are the master key, the singular innovation that unlocks the entire economic model for our future among the stars. Think of them as the foundation upon which every other ambition is built. Without this radical new energy source, the costs of transportation remain impossibly high. Self-sufficiency is a fragile dream, and new industries are merely science fiction. But with it, the entire financial equation flips. The cost of moving people and goods across the solar system plummets, enabling a true interplanetary marketplace. Colonies can achieve genuine self-sufficiency, mining their own water, manufacturing their own air, and growing their own food, no longer dependent on a fragile supply line stretching back to Earth. This is the catalyst that will ignite the greatest economic expansion in human history, a boom that will not be confined to one world but will ripple across millions of miles of space, creating frontiers of opportunity that will inspire and employ generations for thousands of years to come. We have spent centuries looking up at the night sky and wondering what was out there. The question is no longer if we will become a true spacefaring species, but how soon this fusion-powered engine will allow us to finally pay our own way. The future is not just bright, it is waiting, and it is powered by the same fire that lights the cosmos.